is Combinatorial Coding Part 3. Now in my earlier video I had mentioned about the necessity of using a heuristic while performing a search, which is basically your tree search or your binary search, but a combinatorial one where the bounds for the information always contain exactly R bits, R ones in it, same as the information to be coded which is given. We perform the same binary search but always ensure that the bits, but that still may not always offer data compression because we have to use a heuristic, but I neglected to venture any kind of a heuristic myself. So here I wish to correct that mistake and rectify that oversight, and I'm offering a simple heuristic which should provide decent compression. I suspect should. So let I be the piece of information to be coded. Now as again, let L be the lower bound and U be the upper bound. Both L and U we always have. Let M be the intermediate point between L and U. So we must always maintain the inequality L less than equal to M less than equal to U while performing the search, with the strict inequality L less than M less than U always maintained, except for the last case of the last repetition or the last iteration, in which case L equal to M equal to U, which will in turn be equal to I, will hold good. So now we can go about if we perform the normal way, the search, then we may not gain much. So in order to speed up the search a little bit, we proceed as follows. If we wish to now the heuristic or the guiding thought behind this particular heuristic is that since L less than equal to M less than equal to U is always true, the number of leading ones in which both L and U differ must decrease as drastically and as rapidly as possible. So that it attains the equality. So at each iteration, when reassigning either U or L, we have to ensure that U and L differ from each other. The number of bits in which U and L differ from each other, both of them having R1s, always decreases by as much as possible. So that should be the guiding idea. So to that end, one possibility may not be the best one, but or the ideal one simple possibility, but the objective must be that if you can come up with something this. Very likely there are lots of other ways of doing it as well, but one possibility is as follows. Now the argument or the algorithm itself follows. First, we know both L and L. We note the bit which is note the fact that whether L is whether the given information I is closer to L or to U with a bit. Okay. Now for this particular case, I am assuming that I is closer to L. Assuming I is closer to L, a similar argument can be made for the case where I is closer to U. Assuming I is closer to L, okay, we first determine M such that L plus U by 2. Assuming I is closer to L now, then U needs to be set to the largest, U needs to be set to the largest to the largest value less than M having exactly R1s in it. Okay. So this has to be set to U. You determine M and set U to the largest value less than M, which has exactly R1 in it. Now basically we have L here, I lies somewhere in between L and U here, and I since I is closer to U, therefore we set U to the largest value less than M, which has exactly R1s in it. Now let the number of bits in which L and I differ leading bits in which L and I match, sorry, not differ, match. Number of leading bits in which L and I match be A, and let the number of leading bits in which that is leading bits in which I and U match be B. Let M equal to maximum of A comma B. That is, we have L here, so we try to give a rough idea. So these are, you have the bit representation for L here, you have the bit representation for I here, and you have the bit representation of U here. Now suppose A bits of, this is A, okay, so A bits here match with this, and this is B. So B bits match here and A bits match here. Now in this case I'm just assuming in this picture A is greater than B. So that means the bit pattern of A bits of L match with A leading bits of I, and B leading bits of U match with B bit. And here in this case this is the simplest, just a possibility here is this is how it is. Now since we would like U and L to approach each other and converge, match as many bits as possible, let M be the maximum of A and B. So we would like both L and U to match in m bits, that is a maximum of a and b. In other words, here since a is more, the difference between a and b, these two bits where they don't match, you have to match them. So how do you go about doing that? It's simple, right? In this case, what do? In these bits, we this value c, the difference between a and b, c equal to, let c be a minus b. Clearly, how do we go about doing it? We note the value of c. Two possibilities arise here: c greater than 0 or c less than 0. As if c greater than 0, let us consider the case where here for u, since we are assigning u here, m to u here, adjusted to the thereabouts where it has r1s in it, there we have already assigned it. Since it differs there, now for those bits in which this is 1, so some bits in L and U will exist for which this is 1 and which this is 1 and this is 0, and thereafter for which this is 1 and this is 0. So within those m bits itself, you can find such combinations. Make the exchange first. Start off with ones only. If you can't find where you cannot make the exchange and you have a 1 here, then what do? You identify, you always move from left to right here, and you identify the first 0 past the m bits and transfer this 1 to this. Any other exchanges, assuming all exchanges have taken place within the remaining bits of c, c a minus b. Yeah. Then you transfer it always past this to the earliest zeros here, so that you always have u will be greater than or equal to both L and I. That invariant is always maintained. Okay. Now the similar case can occur where c is less than 0, in which case a is less than b. It's just the inverted case here. A similar procedure can be applied there also. Now again, for the case where we are assuming I is closer to L, we have the possibility arises where I is closer to U. A symmetric case only, just as there is symmetry here also, B is greater than in the case where this happens to be more. We can just go through it quickly. So you have here okay, so this happens to be B here, this happens to be B here, this happens to be A here, and this happens to be A here. So B bits of I. Now in this case, the transfer has to be here. For C equal to, C will be these bits. For those bits which we find out the bit patterns differ in these C bits only, we would like at, okay, so now for which this is 0 and this is 1, there is again another case here within those C, these remaining C bits. If there is a case where this should be this is 1 but this is 0, right? So the bit, since this should be 0, you transfer this 1 to this one, so that in order to make it this. But if there is none which occurs here, since we would like C to be minimum, L to be as small as possible, identify the rightmost 0 here and transfer the 1 to the rightmost 0. In this case, where it is. So it is a symmetric case to the previous case B noted. So like again, another symmetric case possibility is what happens if I is closer to U. That is before assigning, right? Before assigning M to U, what if I is closer to U? Then after that you assign M to U, and then what you do? You assign M to the assign to you the smallest R combination, smallest value less than M, which has exactly R1s in it. You assign that to you, and to L, what you will have to assign then? You have to assign the value for the symmetric case. Where L has to be assigned to the value largest value less than L, which has exactly less than M. L has to be assigned the value largest value less than M, where M is equal to L plus U by 2, largest value less than M, which has exactly R1s in it. Now you can again perform the same repetition, or since now M bits always match in L, I and U, that is where M is the maximum of A comma B. So either you can cut off this and recurse here for this new values of L, I and U, or you can continue with the repetition. So in each case M will just keep increasing, that's all. Either you can choose to recurse, or you can choose to iterate. You can either choose to cut out this information and decrease n the number of ones in it, the length of the information, which is, suppose if it is n, so you decrease it by m, or and and the value of r you decrease by the number of ones in that leading m bits, and then recurse it. Or you can continue as is only and repeat only with the new values for L and M without actually cutting down the length of the information and the bounds as well. You could try either approach. Now this is only for the binary case, which could serve as a possible decent heuristic. Now in addition, owing to the fact that if I'm not sure whether it will work, because we know that NCR equal to NC n minus R, but if by complementing either of or all of this also you are able to speed up the process, where the number of matches occurred, mismatches will be actually a lot lesser, in that could also help. You could try seeing if that also works out. Similarly, this is just for the binary case, a possible heuristic that you could use to speed up the search for generating an R combination of n. You can increase the branching factor and make it a ternary search or a quaternary search, and so on. So